Welcome to another episode. Before we begin, I'd love to know where you're listening from and what time it is there. Leave a comment below, and if you enjoy drifting through science and thought like this, you can subscribe to stay with us for more nights of discovery. Now, imagine the ground beneath you. The quiet floor, the still streets, the bedrock beneath cities. All of it feels motionless. But it isn't. Deep under your feet, the planet never truly rests. It moves, grinds, slips and bends. It hums with tension, storing energy like a coiled spring that has been tightening for centuries. Then, one day, without warning, that tension breaks free. The earth shudders, buildings sway, oceans pulse. The very crust of our world ripples like fabric. To us, it's chaos. To the planet, it's a natural rhythm. A sudden reminder that the ground we trust is alive. Tonight, we're going to descend into that hidden physics. The slow dance of tectonic plates, the snap of frictional locks, the shock waves racing through rock, and the science that allows us to see inside our planet using nothing but its own tremors. This isn't just about destruction. It's about motion, balance, and energy. The language the Earth speaks when it shifts beneath our feet. So get comfortable, let the day fall quiet, and together, let's listen to the heartbeat of a restless planet. If we could stand above the Earth and see it without its oceans or forests, stripped down to its bare stone and scars, we would see something astonishing. Not a still, solid world, but a planet made of fragments. Great slabs of rock, each thousands of kilometers wide, moving slowly across the molten layer beneath, like rafts on a restless sea. These slabs are called tectonic plates, and they make up the lithosphere, the rigid outer shell of the Earth. Beneath them lies the asthenosphere, a weaker, ductile layer of the upper mantle, where heat and pressure allow rock to flow, almost like a very slow liquid. It's this subtle movement, driven by heat from Earth's interior, that sets the entire surface of the planet in motion. The scale is nearly unimaginable. Each plate, whether it's the massive Pacific plate or the smaller Nazca plate off South America, drifts only a few centimeters a year. That's about as fast as your fingernails grow. But over millions of years, those centimeters add up to continents splitting, oceans widening, and mountains thrust skyward. This motion was once invisible to human understanding. For most of history, people believed Earth's continents were fixed in place, like features on a statue. Then, in 1912, a German meteorologist named Alfred Wegener proposed something extraordinary: that continents drifted over time. He called it continental drift. His idea was mocked. How could continents move? Skeptics asked. What engine could push entire continents across the globe? Wegener didn't have the mechanism. He died on an expedition to Greenland in 1930, still convinced he was right. Decades later, the missing evidence emerged from the ocean floor. In the 1950s and 60s, geologists studying magnetic patterns in undersea basalt discovered symmetrical stripes of magnetized rock on either side of mid-ocean ridges. As molten rock rose and cooled, iron minerals aligned with Earth's magnetic field, which reverses polarity every few 100,000 years. These magnetic barcodes recorded new crust forming at ridges and spreading outward. Suddenly, Wegener's drift became part of a grander theory, plate tectonics, the unifying framework of modern geology. The Earth's crust and upper mantle together form the lithosphere, which is broken into about a dozen major plates and several smaller ones. They move because of mantle convection, a slow churning of heat within Earth's interior. Hot material rises near mid-ocean ridges. Cooler, denser slabs sink back into the mantle at subduction zones. It's an enormous, self-regulating cycle, like a planetary breathing pattern, only measured in tens of millions of years. But motion, even slow motion, comes with stress. When plates interact, They don't glide smoothly like skaters on ice. They grind, collide, and drag against each other. The boundaries between them are where the Earth's tension accumulates and where earthquakes are born. There are three main types of plate boundaries, and each tells a different story of creation, collision, or destruction. At divergent boundaries, plates move apart. Here, magma from the mantle wells upward, cools, and solidifies into new crust. The Mid-Atlantic Ridge is a prime example, a chain of undersea volcanoes stretching more than 16,000 kilometers or 10,000 miles from the Arctic Ocean to the southern Atlantic. Iceland sits right on top of this ridge, literally splitting the difference between the North American and Eurasian plates. You can stand in a rift valley there, 1 foot on each continent, feeling the planet's slow expansion beneath your feet. These regions are places of birth. They rarely produce large earthquakes because the crust is thinner and hotter, allowing it to stretch and break more gently. But even here, the Earth murmurs, shallow quakes marking each pulse of new crust. Then there are convergent boundaries, where plates collide. These are the great compression zones, where crust is destroyed or thickened. When an oceanic plate meets a continental one, the denser oceanic crust dives beneath in a process called subduction. This is where the most powerful earthquakes on Earth occur, along subduction zones like the Japan Trench, the Peru-Chile Trench, and the Cascadia subduction zone off North America. Here, two immense slabs press together for centuries, locked by friction, deforming and bulging until, one day, the strain surpasses the strength of the rock. Then, the locked zone slips catastrophically, releasing centuries of stored energy in seconds. The 1960 Chile earthquake, the most powerful ever recorded at magnitude 9.5, happened along such a boundary. So did the 2004 Sumatra-Andaman earthquake, which unleashed a tsunami that raced across the Indian Ocean, claiming more than 200,000 lives. Convergent margins are nature's most violent meeting places, but also the most creative. They form mountain ranges like the Andes and the Himalayas, born of compression that lifts rock skyward. Every mountain, every trench, every volcanic arc tells a story of stress and release repeated through geological time. The third kind of boundary is transform, where plates slide past one another horizontally. These are the faults that define the world's nervous edges. The San Andreas Fault in California, for instance, marks the boundary between the Pacific and North American plates. It moves only a few centimeters a year, but every so often that motion halts, locks, and then lurches forward in an earthquake. The 1906 San Francisco quake, magnitude 7.9, was one such moment. City blocks twisted, rails bent, and fires consumed entire neighborhoods. The rupture stretched nearly 480 kilometers or 300 miles along the fault. Transform boundaries don't create or destroy crust. They simply rearrange it. But their motion is deceptive, silent, gradual, then suddenly catastrophic. Imagine bending a wooden ruler between your hands. It resists at first, flexing but not breaking. Keep pressing, and tension builds invisibly within the material until, with a sharp snap, it breaks. Earth's crust behaves in a similar way. Tectonic plates constantly push, pull, and twist against each other, but friction along their boundaries keeps them from sliding freely. Instead, the rocks deform elastically, storing potential energy like a stretched spring. For decades, centuries, even millennia, that strain accumulates silently. Geologists call this the elastic rebound process, first proposed after the 1906 San Francisco earthquake by American geophysicist Harry Fielding Reid. Reid studied ground displacement along the San Andreas Fault and noticed that the land on either side had shifted several meters relative to each other during the quake. He reasoned that before the earthquake, strain had slowly built up as the crust bent and deformed. Then, When the fault finally slipped, the rock snapped back, rebounding elastically to its original, unstressed shape. This simple insight became a cornerstone of earthquake physics. Stress accumulates gradually due to plate motion, and when it exceeds the frictional strength of a fault, the locked zone fails, releasing that stored energy as seismic waves. The numbers are staggering. A large earthquake can release as much energy as several hundred megatons of TNT, thousands of times greater than the most powerful nuclear bombs ever tested. Yet, because this energy spreads through the ground as vibrations rather than light or heat, we don't see the release, we feel it. The earth moves, the ground waves, and we become aware that the solid world isn't as solid as we thought. To understand the actual moment of failure, the flicker between stillness and motion, we need to look at something called the stick-slip phenomenon. It's a deceptively simple process, yet it governs everything from violin strings to car brakes to tectonic faults. When two rough surfaces press together under stress, they stick because of microscopic irregularities called asperities, tiny bumps and ridges that interlock. As stress increases, the force pressing them together also rises. The surfaces resist sliding until the accumulated shear stress finally overcomes friction. Then, in an instant, they slip. The slip releases the stored energy, but only temporarily. The surfaces catch again at a new set of asperities, and the process repeats. In machinery, this stick-slip motion produces squeaks and vibrations. In the earth, it produces earthquakes. Laboratory experiments with rock samples have shown that this behavior can be reproduced on a small scale. When scientists press two pieces of granite together and apply shear force, the rock doesn't slide smoothly. It jerks intermittently. The stress rises steadily, then drops sharply at failure, creating a miniature earthquake. Scaled up to the size of continents, this same physics operates along faults tens or hundreds of kilometers long. Frictional behavior, however, is complex. It depends not only on pressure, but also on temperature, rock composition, pore fluids, and even the speed of slip. At high slip rates, such as during a large quake, frictional heating can momentarily reduce resistance, allowing faults to slip more easily. This is why some earthquakes propagate faster than others, and why fault zones can experience cascading ruptures. What's remarkable is that the stick-slip cycle links timescales across unimaginable ranges. A single slip event might last less than a minute, but the build-up to that moment can span hundreds or thousands of years. Every earthquake we feel today began as strain that started accumulating long before recorded history. Even now, as you listen, stress is building somewhere under the earth. Perhaps along the San Andreas, or beneath Tokyo, or deep in the subduction zone off the coast of Chile. Geodesists, scientists who measure Earth's shape and motion, can actually see this happening. Using GPS networks, they measure how the ground shifts by millimeters each year as strain accumulates. Some regions creep steadily, others remain locked, barely moving at all. Those locked patches, often called asperities on the fault, are the ones that worry seismologists the most. They're like loaded springs, waiting for the moment they'll uncoil. In Japan, the GeoNet system of more than 1,000 continuous GPS stations tracks the slow drift of the islands as they're squeezed by the Pacific and Philippine sea plates. Before the 2011 Tohoku earthquake, the eastern coast of Honshu had been moving westward, accumulating enormous elastic strain. When the fault finally ruptured, it shifted the seafloor by as much as 50 meters, enough to permanently move the entire island of Japan by about 2 meters eastward. That's the scale of force we're dealing with. Continents subtly bending, then snapping like a bowstring released. It's humbling to realize that every serene landscape hides invisible motion. The calm ocean, the silent desert, the mountains etched in morning light, all are part of a restless crust that never truly stops moving. Each grain of sand, each slab of granite, participates in a slow, unending dialogue of compression and release. And the Earth doesn't hurry. It waits. Centuries of pressure build in silence, preparing for a moment that may last less than a minute. When that moment comes, the planet speaks in waves of motion, in frequencies that ripple through its entire body. To the Earth, it's just a step in its long mechanical rhythm. To us, it's a reminder that solidity is an illusion and that we live upon a moving machine made of rock and fire. Beneath the surface, the Earth is a web of cracks. Some are tiny, running only a few centimeters through local bedrock. Others stretch for hundreds of kilometers, slicing through entire mountain ranges and continental crust. These are the Earth's fault lines, invisible boundaries where its plates express their tension. They are the scars of our planet's motion, records of ancient struggles between pieces of the lithosphere that once pressed, tore, or sheared past one another. A fault isn't a single line, as maps often show. It's more like a zone, a volume of crushed, fractured rock where strain has concentrated over time. The ground on either side moves relative to the other, though most of the time that motion is locked in place by friction. When it breaks free, the sudden movement sends waves through the planet's body, the vibrations we feel as an earthquake. The way those two sides move defines the kind of fault it is. There are three main types, but they're part of a spectrum. Nature rarely draws clean lines. When the crust is being pulled apart, it stretches until something gives way. One block of rock drops downward relative to the other, sliding along an inclined plane. That's a normal fault, and it tells us the crust is under tensional stress, being stretched and thinned. Normal faults dominate in regions where the crust is expanding, like the East African Rift or the Basin and Range Province in the western United States. If you drive through Nevada or Utah, those long mountain ridges and flat valleys are direct evidence of this. Blocks of crust uplifted and tilted along normal faults, forming a landscape that looks like an accordion caught mid-stretch. In these places, earthquakes are frequent but generally moderate in size, as the Earth quietly releases tension while it thins its skin. But in other regions, the opposite happens. The crust is pushed together, shortened, and forced to thicken. Here, one block is shoved upward over another, a reverse fault, or if the slope is shallow, a thrust fault. These are the architects of mountains. Every great mountain belt on Earth, from the Himalayas to the Alps to the Andes, is the result of millions of years of compression along vast thrust faults. When India collided with Asia around 50 million years ago, it didn't stop. It's still pressing northward at about 5 centimeters per year, about 2 inches, crumpling the Tibetan Plateau like a slowly folding carpet. The main Himalayan thrust fault beneath Nepal and northern India marks that collision. It's locked in many places, storing energy that will one day be released in earthquakes as devastating as the one that struck Nepal in 2015, which killed nearly 9,000 people. In these zones, the planet breathes upward. Mountains rise, continents reshape, and quakes remind us that creation and destruction are often the same process viewed from different timescales. Then there are faults where neither side moves up or down, but rather past each other sideways. These are strike-slip faults, born from horizontal shear stress, when two blocks grind in opposite directions. They don't build mountains or valleys, they distort them, twisting river channels, offsetting roads, and slicing landscapes like clean surgical cuts. The San Andreas Fault is the most famous of these, a 1,200-kilometer or 750 miles boundary between the Pacific and North American plates. Standing there, you can almost feel the tension between the two halves of California, moving in opposite directions at a few centimeters per year. Each section of the fault is a patient machine, holding back motion until it can't any longer. And when it does move, it does so with terrifying speed, meters in seconds. In 1857, the Fort Tejon earthquake ripped nearly 360 kilometers, 223 miles, of the San Andreas in a single rupture, shifting the ground several meters sideways. Imagine the entire landscape lurching like a rug pulled beneath your feet. That's the power of a strike-slip fault finally letting go. Of course, these three types, normal, reverse, and strike-slip, rarely exist in perfect purity. The Earth's surface isn't simple. Stresses overlap, directions vary, and rocks behave differently depending on temperature, depth, and structure. Most faults are oblique, combining vertical and horizontal motion. Some change behavior along their length, acting as normal faults in one region and strike-slip in another. Fault systems intertwine, branch, and reconnect, forming geometries more like tangled veins than straight lines. If you could peel away the crust and look at them in 3 dimensions, you'd see a labyrinth, fractures linking across scales from microscopic cracks to continental breaks. To study this invisible world, scientists use the patterns of the earthquakes themselves. When a quake occurs, it sends seismic waves through the planet. By recording those waves at stations around the world, seismologists can determine not only where and how deep the rupture began, but also the direction in which the fault slipped. They do this by analyzing the first tiny motions recorded on seismograms, the initial push or pull as the fault snaps. Each seismic station feels either a compressional push or a dilational pull, depending on its position relative to the fault's movement. If you map those first motions in all directions around the epicenter, you get a pattern that looks like a sphere divided into 4 lobes, 2 where the ground was pushed, 2 where it was pulled. This pattern is called a focal mechanism, often drawn as a beach ball symbol on earthquake maps. The dividing lines on that sphere correspond to 2 possible planes in the Earth. One is the actual fault plane that slipped. The other is a mirror image, known as the auxiliary plane. From this geometry, scientists can infer the type of faulting that produced the quake, whether it was normal, reverse, or strike-slip, and the orientation of the stresses that caused it. The focal mechanism gives rise to what seismologists call P and T axes, shorthand for the directions of maximum compression P and maximum tension T during the quake. If you imagine squeezing a ball of clay until it fractures, the P-axis points in the direction of the squeeze, and the T-axis points where it's being pulled apart. By compiling data from many earthquakes, researchers can map these stress orientations across entire regions, revealing how the Earth's crust is being deformed over time. It's a kind of planetary MRI, each earthquake a brief flash of information, each fault a part of the skeleton we can only glimpse when it moves. This method has shown us that fault zones are rarely isolated. Instead, they interact like a living network, each storing and releasing energy in response to the others. When one fault ruptures, the sudden redistribution of stress can push nearby faults closer to failure. This is why earthquakes sometimes come in clusters, one event subtly nudging another, days or even decades later. The 1992 Landers earthquake in California, for instance, ruptured not one fault but 5 in quick succession, jumping across the desert like falling dominoes. Each segment failed within seconds of the next, extending the rupture over 70 kilometers or 42 miles. This cascading behavior challenges our old notion of earthquakes as single, isolated events. They are instead parts of larger systems, dynamic, interacting, and sometimes capable of chaining together in ways that make prediction nearly impossible. The complexity doesn't end there. Faults don't slip in uniform ways. Some portions may move gently, what geologists call aseismic creep, sliding steadily without generating significant shaking. Other sections remain locked, accumulating strain that can only be released suddenly in an earthquake. At the boundary between these two zones, stress concentrates, and small quakes often swarm like whispers before the main rupture. These micro-events are like the sound of fabric tearing before it rips completely. Even within a single fault, conditions vary dramatically with depth. Near the surface, rocks are cold and brittle, snapping under stress. Deeper down, where temperatures and pressures are higher, they become ductile, deforming slowly instead of fracturing. This transition, called the brittle ductile boundary, marks the lower limit of most earthquakes, typically 10 to 20 kilometers or 6 to 12 miles beneath the surface. Below that, the rocks flow too easily to accumulate enough elastic strain for a sudden rupture. It's as if the Earth's crust has two personalities, a rigid, fragile skin floating on a more flexible interior. At the microscopic scale, fault zones are even more intricate. Rocks ground against each other are pulverized into fine powder known as fault gouge, which can act either as a lubricant or a sealant depending on its composition. Fluids, water, carbon dioxide, even superheated brines circulate through these crushed zones, altering minerals and changing frictional properties. Over time, faults heal and strengthen, only to break again. This slow chemical dance can determine how easily a rupture starts and how far it travels once begun. Some of the most revealing evidence about fault behavior comes from places where scientists can actually go inside one. In Japan, the Nojima Fault, which ruptured during the 1995 Kobe earthquake, was later drilled and sampled directly. The cores recovered showed slick, mirror-like surfaces, evidence of intense frictional melting known as pseudo-tachyllite, frozen remnants of rock that had briefly liquefied under the heat of sliding. It's astonishing to realize that an earthquake doesn't just move rock, it can melt it. Temperatures along a fault during rupture can soar to over 1,000 degrees Celsius, even though the motion lasts only a few seconds. Other drilling projects, such as the San Andreas Fault Observatory at depth in California, have allowed scientists to measure temperature, stress, and fluid pressure inside an active fault in real time. These experiments revealed that the San Andreas is weaker than expected, possibly lubricated by pressurized fluids that reduce friction. Such findings challenge long-held assumptions about how faults lock and why some sections produce frequent moderate quakes while others remain quiet for centuries before unleashing a giant one. When viewed from afar, this complexity can seem chaotic, but there is structure in it, a hierarchy of fractures nested within fractures, each governing the next scale up. Tiny cracks merge into small faults, which combine into major fault systems that span entire tectonic provinces. It's this nested geometry that gives the Earth both its unpredictability and its rhythm. Every earthquake begins as a local failure, but is shaped by the stress field of the entire system around it. Sometimes, faults even interact across astonishing distances. After the 2012 magnitude 8.6 earthquake off Sumatra, a rare strike-slip event occurring deep within the Indian Ocean lithosphere, scientists observed a spike in small earthquakes all over the world. They weren't aftershocks in the traditional sense. They were triggered remotely by the passage of seismic waves that slightly changed the stress state on distant faults. It was as if the planet itself flinched in sympathy. Standing on solid ground, we rarely think about the invisible architecture beneath our feet. The planes of weakness that define continents, the scars that trace the planet's restless history. Each fault is a memory, storing evidence of past ruptures, preserving the shapes of ancient quakes that once rattled the world. Some faults have moved hundreds of times over millions of years. Others, like sleeping beasts, may not have awakened since long before humans walked the earth. But none of them are truly still. They wait, slowly gathering the energy that will one day be released again. And that is perhaps the most humbling truth about our planet's fractures. They are not signs of imperfection, but of vitality. They are how a living planet relieves its tension, how it reshapes itself over eons. Without them, there would be no mountains, no valleys, no continents drifting toward one another, no earthquakes to remind us that we live on something that moves. Each fault is both a wound and a mechanism, the Earth's way of maintaining balance while appearing, for the brief span of a human life, completely still. Every earthquake begins in silence. Long before the first tremor reaches the surface, before lamps sway and dishes rattle, a process is unfolding deep within the rock, a quiet and invisible struggle between stress and resistance. The moment a quake starts is called nucleation, the birth of rupture, the instant when a fault that has been locked for decades begins to slip. But what exactly causes that first motion? Why does one fault finally give way while another remains stuck for centuries? To answer that, we have to shrink our perspective, from continents and plates down to the hidden interfaces of mineral grains, pores, and microscopic fractures where the story truly begins. Within every fault zone, there are weak patches, small regions of crushed rock, clay, or fluid-saturated material that can slip more easily than the surrounding mass. These are the seeds of earthquakes. Imagine a fault as a long zipper, most of it jammed tight, but a few teeth slightly misaligned. Those tiny misfits concentrate stress. As tectonic forces keep pushing, the local shear stress rises, deforming the rock on a microscopic scale. At first, the deformation is elastic, reversible. Atoms shift in their lattice, bonds stretch and strain, but the rock still holds. Eventually, though, something gives. A micro crack opens, then another. Each one relieves a little stress, but transfers some to its neighbors. A chain reaction begins. This early stage can last seconds, days, or even years. In laboratory experiments, it's possible to watch it happen. Scientists at facilities like the U.S. Geological Survey's Rock Mechanics Labs or Japan's National Research Institute for Earth Science have used giant press machines to squeeze and shear blocks of granite under controlled stress. They monitor acoustic emissions, tiny clicks of microfractures, as the rock approaches failure. What they see is remarkably consistent: a long, slow build-up of strain, followed by accelerating bursts of small cracks as the system nears instability. Each burst releases a fraction of the stored energy, but together they mark the approach of the critical point, the instant when friction can no longer resist motion. In nature, these same processes occur along faults kilometers deep, where pressure is immense and temperature high. The difference is scale and patience. What takes minutes in a laboratory might take decades beneath a continent. And where lab samples slip by millimeters, natural faults can move by tens of meters. Before the rupture runs free, the fault enters what seismologists call a slow slip phase, a kind of gentle prelude. Here, a small patch begins to creep, slipping a few millimeters or centimeters over hours or days. This slow movement slightly reduces stress on that patch, but it can raise stress on the edges of the slipping zone. If those surrounding areas are close to failure, the creeping patch can trigger their movement too, expanding like an ink stain in paper. At some point, the slipping area reaches a critical size, a few kilometers long depending on depth and rock type, and frictional resistance suddenly drops. The system crosses a threshold from stable sliding to dynamic rupture. What was once a slow, creeping motion becomes an unstoppable cascade. It's a bit like pulling Velcro apart. At first you have to tug slowly. Each hook resists until it lets go with a tiny snap. But once enough of the surface detaches, the rest tears open in an instant. That's how rupture begins, as a runaway instability powered by the very energy it releases. The moment that runaway process starts, the earthquake is born. The speed at which this transition occurs is extraordinary. In large quakes, once dynamic rupture begins, the fault slip can accelerate to several kilometers per second, approaching the speed of sound in rock. The rupture front races along the fault plane, converting potential energy stored for centuries into seismic waves that radiate outward through the crust. Within seconds, kilometers of rock have shifted. Within minutes, hundreds of kilometers. All from a process that began as microscopic cracks joining together in the dark. Still, even among scientists, nucleation remains one of the least understood aspects of earthquake physics. We can describe it, model it, and reproduce pieces of it, but predicting when and where it will happen remains elusive. That's partly because the rock inside a fault is not uniform. Every centimeter is different in mineral composition, fluid pressure, grain size, and temperature. These variations make the system chaotic, sensitive to the smallest disturbances. A pressure change as slight as a few kilopascals, the weight of a person standing on a small patch of ground, can sometimes determine whether a fault fails today or a century from now. Fluids play a particularly mysterious role. At depths where faults are saturated with water or carbon dioxide, the pore pressure between grains can weaken the rock dramatically. High pressure in these tiny spaces reduces the effective friction holding the fault shut. In some cases, natural fluids rising from deeper layers trigger small slips that relieve stress without major quakes. In others, they may prime the system for catastrophic failure. Human activities can sometimes influence this balance too, as seen in regions where wastewater injection or deep geothermal projects have inadvertently triggered earthquakes by altering subsurface pressures. It's a sobering reminder that the Earth's crust is delicately tuned, and that even our modest disturbances can ripple through its stress network. When the fault finally begins to move dynamically, the physical conditions inside it change almost instantly. Shear heating can raise temperatures hundreds of degrees in a heartbeat. Some minerals melt, forming thin glassy layers that act as temporary lubricants. Others undergo rapid chemical changes, releasing gases or weakening phases. The frictional strength of the fault drops even further, allowing the rupture to accelerate. This feedback, stress causing slip, slip causing heating, heating reducing friction, is what gives earthquakes their explosiveness. It's not a simple crack opening, it's a thermomechanical chain reaction. To visualize it, imagine pulling a heavy book across a table. At first, it resists. You increase the force, and it still doesn't move. Then, suddenly, it jerks forward and slides easily before stopping again. That jerky behavior, the sudden transition from static friction to kinetic, is the same principle, scaled up to unimaginable proportions inside the Earth. In some earthquakes, the rupture front even surpasses the local shear wave speed, the speed at which rocks themselves can deform elastically. These rare supershear ruptures behave almost like sonic booms underground, concentrating energy into shock fronts that can amplify shaking on the surface. The 2001 Kunlun earthquake in Tibet and parts of the 2010 Haiti quake exhibited this phenomenon. It's one more reminder that faults are not slow mechanisms, but capable of breathtaking dynamics once unleashed. Still, the beginning, that faint whisper before the roar, remains elusive to measure directly. Seismologists have spent decades trying to detect foreshocks, small tremors that might signal an impending rupture. In some cases, such as the 1999 Izmit earthquake in Turkey, clusters of small quakes occurred near the epicenter in the weeks before the main shock. In others, no precursors appeared at all. Some large earthquakes even begin without warning, their first detectable motion already part of the main rupture. This inconsistency makes forecasting extraordinarily difficult. Nature seems unwilling to follow a script. Laboratory experiments help, but they have limits. In a rock press, everything can be measured precisely: stress, strain, temperature, acoustic emissions. We can see a fault approaching failure, hear its microscopic cracks, and observe the slip unfold in real time. But real faults are enormous. spanning many kilometers, filled with heterogeneities we can't replicate. The scale difference isn't just physical, it's statistical. At small scales, a few fractures dominate behavior. At geological scales, millions of fractures interact, averaging out randomness, but also creating new kinds of emergent behavior, patterns that no single sample could reproduce. That's why, even with modern instruments, the leap from laboratory physics to natural earthquakes is still one of seismology's biggest challenges. We can model the stress field, measure surface deformation with GPS and satellites, and drill into active faults to sample conditions directly. Yet the precise moment of nucleation remains hidden, a secret kept beneath kilometers of rock. In recent years, scientists have begun listening more carefully to the noise in Earth's vibrations, looking for subtle patterns that might reveal a fault's preparation phase. Using dense arrays of seismometers and machine learning algorithms, they've detected tiny, continuous tremors, sometimes called slow earthquakes, that occur too gradually for humans to feel. These events, lasting hours to days, release strain without catastrophic rupture. They might represent faults rehearsing their motion, a kind of silent slip that stabilizes one region while transferring stress to another. In subduction zones like Cascadia, slow quakes have become one of the key indicators scientists monitor, hoping they may hint at how close the region is to its next major event. It's fascinating and humbling to realize that the Earth sometimes chooses to whisper rather than shout. Not every strain release is violent. Some are graceful, invisible, and slow, slipping so quietly that only instruments can perceive them. And yet, these quiet events might hold the key to understanding the loud ones. In the end, an earthquake begins when the conditions align perfectly, when stress, weakness, and friction meet in just the right configuration. It's the culmination of thousands of variables interacting in a single moment. We can predict the general patterns, where large quakes are likely to happen, how often, what magnitude they might reach. But the exact moment when a rupture starts, that first crack, still defies us. Maybe that's appropriate. After all, earthquakes remind us that the planet is not a machine we can control or fully forecast. It's a living, evolving body governed by physical laws, but layered with complexity beyond our complete grasp. Each quake begins as a whisper in the dark, a tiny slip somewhere deep below that grows into motion powerful enough to move continents. And when we feel that motion on the surface, that brief shaking underfoot, we're really feeling the echo of a microscopic decision made kilometers below, where stress finally overcame strength and the Earth decided to move. Once the rupture begins, it doesn't wait for permission. The fault that's been locked for centuries suddenly turns fluid with motion. Stress drops, pressure shifts, and a wave of failure sweeps outward through the rock. This moving boundary, the rupture front, is the heartbeat of an earthquake. It races through the fault at several thousand meters per second, roughly 6,000 to 10,000 feet per second, a traveling zone where friction gives way to slip and stored energy becomes motion. It's difficult to imagine such speed inside solid stone. In a typical earthquake, the rupture front travels at about 2 to 3 kilometers per second. That's around 1.5 to 2 miles per second, faster than a rifle bullet, though still slower than the speed of the seismic waves that follow. In rare cases, it goes even faster, overtaking its own shear waves in what scientists call supershear rupture, the underground equivalent of a sonic boom. When that happens, energy concentrates into a shock front that radiates outward, greatly amplifying the shaking at the surface. Such events are uncommon, but they've been confirmed in a few remarkable cases. The 2001 Kunlun earthquake in Tibet, parts of the 2010 Haiti quake, and the 2018 Palu event in Indonesia, where the rupture tore through the Sulawesi fault at astonishing speed. The seismograms from those events recorded sharp, abrupt signals. the Earth's own version of a crack of thunder following lightning. To picture how this works, imagine that a fault isn't a smooth crack, but a jagged one, covered in countless microscopic high points, tiny ridges of rock called asperities, that keep the two sides locked together. These asperities bear nearly all the stress between the plates. As the rupture front moves along the fault, it shatters them one after another, like teeth breaking off a gear. Each broken contact releases a burst of energy, sends out a pulse of vibration, and clears the path for the next. In a sense, an earthquake is the collective failure of millions of these tiny contact points, each surrendering its grip in milliseconds. But friction doesn't vanish instantly. As the fault slips, the crushed rock between its sides, a powdery mix known as fault gouge, undergoes incredible deformation. Mineral grains grind, slide, and shear against each other, generating enormous heat in a layer sometimes no thicker than a few centimeters or an inch or two. Even at modest slip speeds, temperatures can rise by hundreds of degrees per second. If that heat can't escape quickly enough, portions of the fault actually begin to melt. Thin, glassy streaks known as pseudotachyllites are the frozen remains of those brief molten moments, geological signatures of faults that once liquefied under stress. They've been found in ancient fault zones all over the world, silent evidence of past earthquakes that grew hot enough to turn rock into fluid for just a few seconds. This heating triggers another process called thermal pressurization. Most fault zones contain fluids, water, carbon dioxide, even hydrocarbons, trapped in the tiny pores of the rock. When the fault suddenly heats up, those fluids expand or vaporize, sharply increasing the pressure within the pores. That pressure pushes back against the rock walls, reducing the effective stress that keeps the two sides pressed together. With less resistance, the fault becomes slippery, almost lubricated, and the slipping accelerates even more. It's a runaway feedback loop. Motion creates heat, heat weakens the fault, and weakness allows more motion. This feedback explains why earthquakes can spread so efficiently once they begin. The energy stored for centuries doesn't simply vanish into heat. Much of it converts into organized motion, the seismic waves that radiate outward through the crust. Still, a large portion is lost to friction, grain crushing, and microscopic deformation along the slipping surfaces. That inefficiency is a blessing. It's one reason the Earth doesn't tear itself apart. Most of the energy stays localized along the fault, but the small fraction that escapes as vibration is enough to shake cities hundreds of kilometers or hundreds of miles away. A good way to imagine it is to think of striking a drum. Most of the force from your hand stays in the drumhead, absorbed as tension and heat, but part of it escapes as sound. In the same way, most of the fault's energy remains buried in the rock, but a small portion radiates outward as seismic waves, the sound of the Earth. Some frequencies shake tall buildings, others rattle small ones, and together they create the complex pattern we feel as ground motion. How the rupture front moves, its direction, its shape, its interruptions, determines how that shaking is distributed. When the front bends or curves, it can focus energy into specific directions, amplifying motion in some areas while sparing others. During the 1999 Izmit earthquake in Turkey, the rupture raced eastward, and towns directly in its path suffered far greater shaking than those behind or beside it. It wasn't just the size of the earthquake that mattered, it was the geometry and timing of the rupture itself. A fault, after all, is rarely neat. It's a maze of bends, steps, and splinters, structures that can slow, stop, or redirect the rupture. When the front hits one of these barriers, stress builds there, and sometimes the rupture pauses before leaping onward. Each restart releases a burst of higher frequency energy, producing the sharp, jerky shaking that makes earthquakes feel unpredictable. In some cases, the rupture even jumps to neighboring faults, triggering a chain of breaks that unfold across vast regions. The 2016 Kaikoura earthquake in New Zealand did just that. More than a dozen separate faults ruptured in sequence, the energy zigzagging through the landscape like lightning through a thundercloud. In the milliseconds of each slip, the rock at the contact surfaces undergoes transformations almost chemical in intensity. The frictional heat can drive minerals to release gases, form new compounds, or even melt briefly. Certain rocks, such as serpentinite or talc, become extremely weak under shear, acting like slick clay that helps the fault glide. Others, like quartz-rich granite, resist until the last moment, building higher stress and heat before failing. This variety explains why some faults slip gently and often, while others stay locked for centuries before breaking catastrophically. Modern research has even measured the faint warmth left behind by large quakes. After the 2011 Tohoku earthquake in Japan, scientists drilled into the fault under the seafloor and found it still a few tenths of a degree warmer than its surroundings, a tiny rise, but proof of the enormous frictional heating that occurred minutes earlier. From that, they concluded that during the quake, the fault's friction had dropped to nearly zero. It slid almost as smoothly as ice on ice. At the heart of all this lies a paradox. A fault must be strong enough to store strain for centuries, yet weak enough to let go in an instant. Reconciling that duality is one of the great challenges of earthquake physics. The answer seems to be that faults evolve. Minerals recrystallize, fluids migrate, old ruptures change the texture of the rock. Each quake alters the fault's memory, priming it for what comes next. It's a living system, one that learns, weakens, heals, and breaks again. Seen in this way, an earthquake is not just a sudden event, but a process. An immense mechanical conversation between strength and surrender. The rupture front is the messenger, sweeping through the crust like a blade of invisible fire, converting stored tension into motion and motion into the trembling we feel above. Then, as quickly as it began, it stops. The fault stills. The waves spread outward. The world settles again, quietly rearranged. And somewhere deep below, the cycle begins anew. The long, silent rebuilding of stress. The patient winding of energy that one day, far in the future, will break free again. To us, it feels like destruction. To the earth, it is simply motion, the oldest motion there is. The sound of a planet restoring balance through the language of fracture and release. When an earthquake happens, what we feel on the surface is only the echo, a translation of what the rocks beneath are trying to say. The rupture itself is over in seconds, but the energy it releases radiates outward through the planet like ripples through water. These vibrations are the Earth's voice, its seismic waves. They travel vast distances, bending, reflecting, and interfering as they go, carrying information about the hidden interior of the planet. Every tremor, every distant quake, is both a destructive force and a message from deep within. Seismic waves come in many forms, but they all obey the same simple idea. Energy moves, matter mostly stays in place. Rocks themselves don't travel far. They oscillate around their resting positions as the disturbance passes through. Yet that movement can be enough to topple buildings, shift rivers, and change coastlines. The physics is pure and unforgiving, motion passing through elasticity, each particle tugging on the next, transmitting stress across unimaginable distances. The first to arrive are the primary waves, or P waves. They're the fastest of all, moving through rock at speeds of 5 to 8 kilometers, or 3 to 5 miles per second, and through the planet's deeper mantle even faster. P waves are compressional. They push and pull the ground in the same direction they travel, much like sound waves in air. As the wave front moves, Particles of rock alternately squeeze together and then stretch apart, creating a rhythmic pulse of compression and expansion. Because of this, P waves can travel through solids, liquids, and gases alike. They're the first warning, often arriving tens of seconds before the damaging shaking begins. In modern seismic networks, those precious seconds can trigger early warning systems that shut down trains, pause surgeries, and send alerts before the surface waves strike. Following behind come the secondary waves, or S waves. These are slower, roughly 3 to 5 kilometers, or 2 to 3 miles per second, and far more destructive. S waves move by shearing the rock perpendicular to the direction of travel, shaking the ground side to side or up and down. Unlike P waves, they can't travel through liquids because liquids can't sustain shear stress. When they reach the surface, they make the ground roll and sway in a way that feels alien, as if the solid earth has turned to gelatin beneath your feet. They're the reason tall buildings oscillate, bridges twist, and mountains seem to ripple. To seismologists, the P and S waves together form the body waves of the Earth, vibrations that travel through its interior, revealing its composition by how they bend and slow. But it's the surface waves, those that skim along the outer layers of the planet, that cause most of the damage. They're slower still, but far more persistent, and they grow in amplitude as they approach the open air. There are two main kinds. Love waves, named after the British mathematician A.E.H. Love, move the ground horizontally, shaking it from side to side in a motion that tears apart walls and collapses masonry. Rayleigh waves, discovered by Lord Rayleigh in 1885, move more like ocean waves, with an elliptical rolling motion that makes the ground rise and fall as they pass. If you've ever watched a solid building move as though it were floating on water, you've seen the signature of Rayleigh motion. Together, these surface waves trap most of their energy near the crust, bouncing between layers like sound between walls, and that confinement makes them especially powerful in populated regions. It's strange to think that when the ground shakes, what we're really feeling are the same kinds of waves that fill the universe. Sound, light, and seismic vibrations are all carriers of energy through a medium. Different frequencies, different forms, but the same universal principle. And like light or sound, seismic waves reflect, refract, and interfere as they travel. The crust and mantle are not uniform materials. They're layered, folded, and patchy, each transition boundary altering the wave's path. When a wave crosses from one layer of rock to another, its speed changes, and so does its direction, just as light bends when it passes from air into water. This bending, or refraction, is why waves curve deep within the Earth, and why their arrival times at the surface can be used to map the planet's internal structure. At some boundaries, such as the interface between the crust and the mantle, known as the Mohorovičić discontinuity, or simply the MOHO, part of the wave's energy is reflected back while the rest refracts downward. This partial reflection creates echoes that seismologists can record and interpret, much like sonar in the ocean. By analyzing these reflections, scientists have been able to chart the thickness of the crust under continents and oceans, revealing that continental crust is thicker, buoyant, and more complex, while oceanic crust is thinner and denser. Deeper still, the same principles have shown that the Earth has a liquid outer core, where S waves disappear entirely, and a solid inner core that bends P waves in predictable ways. All of that knowledge, the very map of Earth's internal layers, comes not from sight, but from listening to how these waves behave. The way seismic waves reflect and refract also determines what we experience during a quake. In mountainous regions, waves can scatter and weaken, absorbed by irregular rock. In sedimentary basins, however, they can amplify dramatically. Soft soils act like amplifiers, trapping energy and increasing the duration of shaking. This is one of the reasons some cities suffer so much more damage than others, even at the same distance from the epicenter. Mexico City, for instance, is built on the clay-rich sediments of an ancient lakebed. When the 1985 Michoacán earthquake struck nearly 350 kilometers away, about 217 miles away, seismic waves reached the city and resonated within the basin. The frequency of those waves happened to match the natural oscillation of mid-rise buildings, around 2 to 3 seconds per cycle, causing them to sway violently and collapse while shorter and taller buildings survived. It was a tragic lesson in resonance, the amplification that occurs when an external vibration matches a system's own frequency. The same principle makes a wine glass shatter when a singer hits the right note. In earthquakes, the singer is the ground itself. Every structure has its own natural frequency, determined by its height, stiffness, and mass. Short, rigid buildings tend to resonate with high-frequency S waves, while tall, flexible skyscrapers respond more to the low-frequency role of Rayleigh waves. That's why different parts of a city can experience entirely different shaking during the same event. In San Francisco, during the 1989 Loma Prieta earthquake, some buildings on bedrock sustained minor damage, while those built on soft fill near the bay were devastated. The soil beneath them acted like a drumhead, amplifying the low-frequency surface waves. In Tokyo, engineers designed skyscrapers with tuned mass dampers, giant counterweights that sway opposite to the building's motion, to prevent resonance from building up. It's an extraordinary case of human architecture learning the same physics that governs the planet itself. The way waves reflect can also cause interference, where multiple waves overlap, reinforcing or cancelling each other. In some places, the interference creates zones of especially strong motion, called focusing effects. In others, waves arrive out of phase, reducing shaking. This is why an earthquake can topple one building while leaving another, only a few hundred meters away, relatively unharmed. It's also why underground structures, tunnels, and pipelines can experience complex stress patterns as different wave modes combine in unpredictable ways. One of the most haunting aspects of seismic waves is how long they persist. After the main rupture has ended, the Earth continues to vibrate for minutes, even hours, as energy bounces within the planet. Large earthquakes can set the entire globe ringing like a bell. After the 2004 Sumatra-Andaman event, sensitive instruments detected oscillations in Earth's shape lasting for weeks. These global vibrations, called normal modes, have periods of thousands of seconds. They're too slow to feel, but they tell us that the whole planet responds elastically to its own quakes, a reminder that the Earth, solid as it seems, is capable of movement on scales that dwarf our comprehension. The beauty of this science lies in how it transforms destruction into knowledge. Every wave, no matter how violent, carries information. By measuring how fast P and S waves travel, scientists can infer rock density, composition, and temperature. By comparing arrival times at different stations, they can triangulate where a quake began and how the rupture unfolded. Networks like the Global Seismographic Network, with stations on every continent and island, have turned the Earth into a vast listening device. The signals from each quake are stored, analyzed, and even used to study other planets. When NASA's InSight mission placed a seismometer on Mars, the first Marsquakes it detected revealed the red planet's crust and mantle in precisely the same way we learned about our own. It's poetic, the method born from our planet's violence, now helping us understand the quiet rhythms of others. But the same knowledge also keeps us safe. Modern early warning systems depend on the fact that P waves arrive before the more damaging S and surface waves. By detecting that first arrival and calculating the likely intensity of the shaking that follows, systems in Japan, Mexico, and California can issue alerts seconds in advance, enough time to stop trains, shut gas lines, or simply tell people to take cover. It's not prediction, it's physics applied faster than the fault can act. Even with this understanding, the experience of seismic waves is profoundly humbling. When the ground moves beneath us, our instincts rebel. We rely on the earth to be solid. But during a quake, that trust is briefly broken. You feel the P wave first, a faint, almost harmless jolt, like a heavy truck passing by. A few seconds later, the S wave hits, rolling through like a deep breath from below. Objects sway, windows creak, lights swing in unison. Then the surface waves arrive, slow, powerful, rhythmic, and the world seems to move as one, buildings and streets undulating together. It's as if the planet is flexing, reminding us that solidity is an illusion maintained only by scale and time. Not all waves reach us with such power. Many die out unnoticed, absorbed by the crust or scattered into harmless background motion. For every quake that devastates a city, countless others release their energy quietly beneath the ocean or deep in the desert where no one feels them at all. These silent quakes are the majority, the planet's normal rhythm, the murmuring heartbeat of tectonic life. Only occasionally do we become aware of it. In the end, seismic waves are the Earth's way of breathing out after holding tension for too long. They are both the evidence of stress and the act of release. Through them, we've learned more about our planet's interior than any drill could reach, and they remind us, every time they pass beneath our feet, that we are living on a resonant body, a sphere of stone and heat that rings with its own music, audible only when it moves. When we listen to that music with instruments instead of fear, we begin to understand not only earthquakes, but the vast, elastic life of the Earth itself. Every earthquake does more than shake the ground. It also illuminates the invisible. When seismic waves race through the planet, they don't just carry destruction, they carry information. Their paths bend, slow, or vanish altogether depending on what they pass through, and in those subtle distortions lies the blueprint of the Earth's interior. By listening to these echoes, seismologists have built a map of the world beneath our feet, a world no human eye will ever see directly. For most of history, people could only imagine what lay below the crust. Ancient thinkers spoke of fire, water, or empty caverns. Even in the early 20th century, the deep Earth was a mystery. We had dug barely 12 kilometers, or 7.5 miles into the crust, not even a fraction of a percent of the planet's radius. But in 1906, British seismologist Richard Dixon Oldham made an observation that changed everything. He noticed that after large earthquakes, seismographs recorded 3 distinct sets of waves arriving at different times. The first were fast, compressional waves, P waves. Then came the slower shear waves, S waves, and finally long rolling surface waves. But curiously, for stations far from the epicenter, more than about 100 degrees away, or 11,000 kilometers, 6,800 miles, no direct S waves arrived at all. They simply vanished. Oldham realized that something inside the Earth must be preventing S waves from passing through. Since S waves can't travel through liquid, he deduced the existence of a liquid core, a molten sphere surrounding the planet's solid center. It was one of the first major insights into Earth's structure, all derived from timing differences on sheets of paper inked by mechanical pens. 2 decades later, in 1936, Danish seismologist Inge Lehmann took that idea further. While studying wave arrivals from distant earthquakes, she noticed faint P-wave reflections appearing where none should exist, inside the core's shadow zone. After painstaking analysis, she proposed that the Earth's core wasn't entirely liquid after all. Instead, it had a solid inner core nested within a liquid outer one. Her conclusion, radical at the time, was later confirmed by increasingly precise measurements. The Lehmann discontinuity, the boundary she revealed, remains one of the defining discoveries of seismology. Those 2 breakthroughs, Oldham's liquid outer core and Lehmann's solid inner one, came entirely from how seismic waves behaved in what we call shadow zones. If you plot the arrival of P and S waves around the globe after a major quake, you find two mysterious gaps. S waves disappear beyond 103 degrees from the source, unable to pass through the liquid core. P waves, which can travel through liquids, still arrive, but there's a gap between roughly 103 and 142 degrees, an area where they're refracted so sharply by the liquid core that none reach the surface. That region is the P-wave shadow zone. Only beyond 142 degrees do the refracted waves emerge again, bent inward by their passage through the core. It's from this bending, these invisible deflections, that we know not just that the core exists, but roughly how big it is, about 3,500 kilometers or 2,200 miles in radius. It's extraordinary to think that the deepest parts of the Earth were discovered not by digging, but by listening. Each earthquake sends out pulses that travel through every layer of the planet, and by measuring their arrival times at stations across the globe, scientists can infer how fast they moved, and therefore what kind of material they passed through. Denser, stiffer rocks let waves travel faster. Molten or partially molten zones slow them down. Where waves bend, reflect or vanish, we find boundaries, like the crust-mantle boundary, the moho, the core-mantle boundary, and even smaller transitions deep within the mantle. Together, these boundaries form a kind of layered architecture, a planet structured not randomly, but with depth, rhythm, and composition. As technology advanced, seismologists began to treat the Earth like a medical patient undergoing a scan. Instead of X-rays, they used earthquake waves. Instead of a detector on one side, they used thousands of sensors spread across continents. The result is seismic tomography, a three-dimensional image of the Earth's interior, created by analyzing how waves speed up, slow down, or curve along their paths. It's the same principle as a CT scan in medicine, only scaled up to a planet. To build such an image, computers process thousands of earthquakes, tracing millions of wave paths through the Earth. Each path samples a different portion of the interior, and by combining them all, scientists can reconstruct variations in temperature and composition. Where waves move faster, the rock is cooler or denser. Where they move slower, it's hotter or partially molten. From this, a vivid picture emerges, descending slabs of subducted oceanic crust diving deep into the mantle, vast upwellings of hot material beneath Africa and the Pacific, and the swirling convection currents that drive plate tectonics itself. The Earth, once thought to be static, now appears as a living, circulating system, a vast conveyor of heat and rock rising and sinking over millions of years. One of the most striking findings of seismic tomography is how far subducted slabs can penetrate. Some extend all the way to the core mantle boundary, 2,900 kilometers or 1,800 miles deep, forming cold tongues of dense material in an otherwise fiery mantle. These slabs sink slowly, taking millions of years to reach those depths, and may influence how heat escapes from the core. Above them, giant mantle plumes rise, columns of hot, buoyant rock that can create volcanic hotspots like Hawaii or Iceland. Their existence was long suspected, but only confirmed when tomography showed narrow vertical zones of low seismic velocity beneath them, like chimneys feeding heat from the deep mantle to the surface. The Earth, it turns out, has its own slow heartbeat of rising and sinking material, an internal weather system made of rock instead of air. Seismic imaging has also revealed how uneven the core mantle boundary really is. It's not a smooth shell, but a rugged, dynamic landscape with mountains and valleys thousands of meters high, all made of different materials. In some regions, thin patches of ultra-low velocity zones may represent molten silicate or pockets of metallic iron, strange hybrid layers bridging solid and liquid states. These regions might be the source of mantle plumes or the remnants of ancient slabs that melted long ago. Every new dataset adds detail to this unseen world, turning our mental picture of the Earth from a static cross-section into a dynamic, ever-changing planet. Beyond Earth, the same techniques are now helping scientists probe the interiors of other worlds. The seismometers on Mars, deployed by NASA's InSight mission, detected small Marsquakes that allowed researchers to estimate the thickness of its crust and the size of its core, roughly half the diameter of Earth's and probably molten. For the first time, we've used another planet's own tremors to look beneath its surface. The method that once revealed Earth's inner core now maps the hearts of alien worlds. It's humbling to think that every major step in our understanding of the planet's structure has come from the same source, the Earth itself speaking through its vibrations. Each quake, no matter how distant, contributes another piece to the puzzle. The data from a large earthquake recorded across hundreds of stations can be inverted into detailed 3D models, showing not only static layers but movement, the flow of rock in the mantle, the tilt of slabs, even the oscillations of the inner core. We now know that the inner core itself may rotate slightly faster than the rest of the Earth, completing an extra rotation every few decades. Even that was discovered not through direct observation, but through subtle changes in the travel times of seismic waves crossing the planet. In a sense, the Earth has become its own instrument, a vast resonating sphere constantly recording and transmitting information about its insides. And in every tremor, scientists read the same message, that our planet is alive with motion from crust to core, its layers interacting, circulating, exchanging energy across eons. The next time the ground moves and you feel that brief wave beneath your feet, remember, those same vibrations will travel through the entire globe, bounce off the core, and return as whispers that tell us what the Earth is made of. Each earthquake is not just an ending, but an observation, a flash of insight that lets us see for a moment into the beating heart of the world. Most earthquakes come from shallow depths, a few kilometers down, within the brittle crust where rocks can break easily. But some come from much farther below, deep in the mantle, hundreds of kilometers beneath our feet. At those depths, the pressure is so immense, the rock so hot, that it shouldn't be able to fracture at all, and yet it does. These are the deep focus earthquakes, rare, mysterious, and among the strangest phenomena on Earth. When seismologists mapped the locations of earthquakes around the world, they noticed a remarkable pattern. In certain regions, particularly around the Pacific Ocean, quakes didn't just occur near the surface. They formed inclined planes sloping down into the Earth, sometimes reaching depths of 600 or even 700 kilometers or 430 miles. These zones, named after Japanese scientists Kyu Wadati and Hugo Benioff, became known as Wadati-Benioff zones. They mark the descent of oceanic plates as they sink beneath continental ones, dragged into the mantle by the slow machinery of subduction. If you could see one of these zones in cross-section, it would look like a glowing ribbon cutting into the planet, a diagonal line of seismicity tracing the downward path of a dying plate. Near the surface, quakes are frequent and violent, where the plates grind and jam. Deeper down, the earthquakes grow fewer but still persist, following the slab-like echoes trailing behind a sinking ship. At first glance, that shouldn't happen. By 100 kilometers or 60 miles deep, rock behaves more like warm wax than brittle glass. By 400 kilometers or 250 miles, it's under pressures exceeding 13 gigapascals, enough to crush steel. How can it still break? To understand that paradox, we have to look at what happens to a subducting plate as it descends. An oceanic plate begins as dense cold basalt formed at a mid-ocean ridge. Over millions of years, it cools and thickens. When it finally sinks into the mantle, it carries that coldness with it, a slab hundreds of degrees cooler than the surrounding rock. As it plunges downward, it remains mechanically strong, at least for a while, resisting deformation even as it's squeezed from all sides. Inside that cold slab, the conditions are just right for earthquakes to continue. The pressure is enormous, yes, but the temperature is still low enough for the rocks to remain brittle. It's like pushing an icicle into a furnace. The surface melts, but the core stays cold a little longer. But temperature alone can't explain how brittle failure occurs where materials should flow. One key lies in dehydration embrittlement, a process driven by the release of water from minerals. Many of the rocks in a subducting plate contain hydrous minerals like serpentine, amphibole, or lawsonite, which have water locked inside their crystal structures. As pressure and temperature increase, these minerals break down, releasing water into the surrounding rock. The freed fluids drastically reduce the effective stress between grains, lowering friction and allowing sudden failure even under immense pressure. In essence, the rock momentarily loses its strength. It becomes wet and weak. A tiny slip can then cascade into a full rupture, producing an earthquake deep beneath the mantle. These dehydration reactions occur at specific depths, which correspond closely to clusters of observed deep quakes. It's as if the slab itself is sweating under pressure, and each pulse of released water triggers a tremor. Dehydration may explain quakes down to around 300 kilometers or 190 miles, but deeper than that, another process must take over. At around 400 to 700 kilometers, about 250 to 430 miles, the subducting slab crosses a series of mineral transformations known as phase changes. Here, the minerals that make up the mantle, primarily olivine, the green crystal that dominates the upper mantle, rearrange their atomic structures into denser forms. Olivine first transforms into wadsleyite, then ringwoodite, and finally into bridgmanite and ferropericlase, the main minerals of the lower mantle. These changes aren't gradual, they happen abruptly, releasing or absorbing energy. Under the right conditions, the transformation can generate localized stress and micro-cracking, another way to trigger failure in otherwise ductile rock. Some scientists think that as olivine transforms, it briefly creates weak spots where strain can concentrate, producing deep earthquakes up to 700 kilometers or 430 miles below. It's a fascinating idea that the atomic rearrangement of crystals, invisible and instantaneous, could send shock waves through the entire planet. These processes explain why earthquakes don't occur beyond about 700 kilometers. Below that depth, the pressure and temperature are simply too high. The minerals have all converted into forms that deform plastically, flowing instead of breaking. There, the mantle moves like slow honey, convecting over millions of years, not snapping in seconds. That boundary, around 700 kilometers or 430 miles down, represents the brittle ductile transition at the deepest possible extreme. Below it, the Earth is silent. The absence of quakes there isn't just a detail, it defines the mechanical behavior of our planet. It marks the point where rocks lose their ability to store elastic strain, where they stop behaving like brittle materials and start behaving like fluids that creep and fold. It's the limit of Earth's capacity for sudden motion. Everything below that moves in geological time. Deep earthquakes, then, are the ghosts of the surface world, the echoes of oceanic crust descending into heat and pressure it was never meant to survive. They remind us that subduction is not a gentle process, but a recycling one, the crust returning to its source, carrying its flaws and fractures deep into the mantle until even they can no longer exist. And although we'll never feel these quakes directly, their waves reach us, whispering stories of a realm beyond fracture, where rock still tries to break one last time before surrendering to flow. Each deep tremor is a sign that the Earth's old crust is dying in motion, still speaking in the language of strain and release, even as it melts into the planet that made it. It's hard not to feel awe at that. the final shudder of a plate vanishing into darkness, its last attempt at movement before becoming something else entirely. Down there, nearly 3/4 of the way to the core, earthquakes come to an end. The planet keeps moving, but not in jolts or cracks anymore, only in slow, eternal convection, as if the deep Earth has remembered patience again. When you look at the planet's surface from far enough away, earthquakes seem like random events, scattered dots on a map, unpredictable in time and place. But step back even farther, or better yet, look with mathematics instead of eyes, and a pattern begins to emerge. It's faint, elegant, and strangely universal. For all their apparent chaos, earthquakes obey laws, not human laws, but statistical ones written deep into the behavior of complex systems. Through them, the Earth reveals a subtle rhythm behind the disorder. One of the first people to glimpse that rhythm was Benno Gutenberg, a German seismologist working in the early 20th century. He noticed something curious in the data from global earthquakes. Small quakes were far more common than large ones, but their relative frequencies followed a consistent pattern. Together with Charles Richter, who later created the famous magnitude scale, he formulated what became known as the Gutenberg-Richter law. The law is simple to state. It says that if you take all the earthquakes in a region and plot how many happen at each magnitude, the number of quakes drops by about a factor of 10 for every one-step increase in magnitude. So for every magnitude 6 earthquake, there are roughly 10 of magnitude 5, 100 of magnitude 4, and 1,000 of magnitude 3. Across the world, that ratio stays astonishingly consistent. It's as if the Earth follows a universal rule of proportion, a fractal pattern repeating across scales from the barely perceptible to the catastrophic. This relationship tells us something profound. There is no characteristic earthquake size. The same physical process governs both the smallest tremors and the largest megathrusts. A magnitude 9 earthquake is not a different kind of event, just a much larger version of the same mechanics. The Earth's faults, like the flicker of fire or the crackle of static, operate on what scientists call a scale-free principle. Energy release is continuous across magnitudes, without a clear dividing line between the minor and the monumental. But earthquakes don't occur one by one. They come in families: foreshocks, main shocks, and aftershocks, and even those follow a mathematical rhythm. If you record the number of aftershocks that follow a major quake, you find that they decay in time following another elegant pattern first discovered in 1894 by Japanese seismologist Fusakichi Omori. He found that the number of aftershocks decreases roughly as one divided by the time since the main earthquake. So there are about 10 times fewer aftershocks after 10 days than after 1 day, and about 100 times fewer after 100 days. This is called Omori's law, and like Gutenberg and Richter's discovery, it holds true almost everywhere on Earth. It's as if the crust takes a long, slow breath after each rupture, releasing its energy in diminishing waves of relaxation. These two relationships, Gutenberg, Richter, and Omori, can actually be combined. Together, they describe not just how earthquakes are distributed by size, but how they evolve in time. The crust behaves like a system of linked springs and frictional locks, where each slip redistributes stress to its neighbors. One earthquake triggers others, which in turn may trigger more, forming a cascading chain reaction. Most of the time, those chains stop quickly, small quakes triggering only a handful of others. But occasionally, the chain runs away, linking hundreds of small failures into one massive rupture. It's the same principle that governs avalanches, forest fires, or even electrical breakdowns, a self-propagating process balancing on the edge between order and chaos. In the late 1980s, physicist Per Bach and his colleagues realized that this kind of behavior wasn't unique to earthquakes. They demonstrated it with a simple computer model of a sand pile. You drop grains of sand, one at a time, onto a flat surface. At first, nothing happens. The pile grows steeper until suddenly a single grain causes a small slide. Most slides are tiny, but every once in a while, one cascade connects across the entire pile, producing a large avalanche. You don't need to fine-tune anything. The system naturally evolves toward a state of critical balance, always on the verge of instability. This is called self-organized criticality, and when you count the avalanches by size, they follow the exact same kind of distribution as earthquakes. Small ones are common, large ones rare, but all sizes exist in between in a smooth, predictable proportion. The Earth's crust behaves in exactly the same way. Tectonic plates move continuously, adding stress to faults grain by grain, like sand falling on the pile. Each fault segment has its own breaking point. Most of the time, stress is relieved locally through tiny slips, microquakes too small to feel. But sometimes, one of those slips sets off a chain reaction. Neighboring patches fail, and the rupture grows, linking into a single large event. The system doesn't need external control. It organizes itself around this delicate critical point, hovering perpetually between stability and failure. That's why earthquake statistics look the same across continents, depths, and centuries. They are not random accidents, but expressions of a universal physical behavior. Seeing earthquakes through this lens changes how we think about them. They're not simply disasters, but manifestations of a planet in dynamic equilibrium. The crust never stops moving. It just alternates between long, quiet accumulations of stress and brief, chaotic releases. Over geological time, those releases are what let the planet reshape itself, lifting mountains, widening oceans, closing seas. From a physical point of view, earthquakes are simply the mechanism by which a slowly driven system maintains balance. And the mathematics of their occurrence, the logarithmic drop in number with magnitude, the 1/time decay of aftershocks, is the statistical fingerprint of that balance. But within that order lies deep unpredictability. Self-organized critical systems are predictable in a statistical sense. We can say how often certain magnitudes will occur, but not in a specific one. We can't predict which tiny slip will become the next giant rupture, just as we can't predict which grain of sand will trigger a pile to collapse. In that way, the Earth behaves like every other complex system governed by feedback and thresholds, deterministic in principle but unpredictable in practice. It follows laws, but those laws don't yield to prophecy. We can know the odds, not the outcome. Foreshocks are a perfect example of this ambiguity. A small quake near a major fault could be a harmless adjustment, or it could be the first whisper of a catastrophe. Statistically, only about 1 in 20 moderate earthquakes turn out to be true foreshocks. The rest are simply part of the background murmur of a restless crust. The trouble is, they all look identical until the larger quake happens. In hindsight, we see patterns everywhere. In real time, everything looks like noise. It's a humbling reminder that nature's simplicity can still outpace our prediction. If you could visualize the Earth's seismicity over time, it would look like a flickering web, clusters of light appearing and fading, each cluster a chain of aftershocks, each bright pulse a main rupture. The web never goes dark. There are roughly 500,000 detectable earthquakes every year, from microshocks in the crust to giant megathrusts in the subduction zones. Their collective behavior follows those same power law curves Gutenberg, Richter, and Omori first described, bridging human scales with planetary ones. It's a kind of heartbeat, irregular but consistent, pulsing with the rhythm of stored and released energy. When scientists model this behavior, the mathematics reappears across disciplines. Forest fires follow the same size-frequency relationships. So do solar flares, market crashes, and even bursts of neural activity in the brain. Each system accumulates tension slowly and releases it suddenly, producing a spectrum of events that looks the same whether you're studying stars, trees, or faults. The pattern is the universal signature of systems poised on the edge of change, not stable, not chaotic, but balanced in between. There's something almost philosophical about that. For all their violence, earthquakes are not exceptions in nature's order. They are the order, written in a language of logarithms and decay. They show us that even chaos has structure, that unpredictability can still follow rules. The planet's shaking is just the sound of equilibrium being restored, not perfectly, not predictably, but always statistically consistent. So, beneath the fear and the destruction, there's a strange kind of peace in knowing this. That the Earth doesn't move without reason, that its chaos is mathematical, and that we, standing on its trembling surface, are part of a system that has always lived at the edge, balancing itself, grain by grain, tremor by tremor, forever finding order in the noise. There are earthquakes, and then there are the ones that rewrite coastlines. Most quakes release enough energy to rattle cities or crack mountains, but a few unleash forces so vast they shift the very geometry of the planet. These are the giants, the mega-earthquakes. They occur rarely, perhaps once or twice in a century, but when they do, the effects echo across oceans, generations, and even in the rotation of the Earth itself. The largest earthquake ever recorded struck on May 22, 1960, off the coast of Chile. It began as a rupture on the boundary where the Nazca Plate dives beneath South America, a subduction zone already famous for producing powerful quakes. At first, it seemed like an ordinary large event, perhaps a magnitude 7 or 8. But as seismographs around the world continued to record the shaking, it became clear that something extraordinary was happening. The rupture didn't stop. It raced along the fault for more than 1,000 kilometers, about 600 miles, from Concepcion to Valdivia, tearing open section after section. For over 10 minutes, the planet shuddered. When it finally ended, the earthquake's moment magnitude was calculated at 9.5, the most powerful in modern history. Entire stretches of coastline dropped several meters. Others rose out of the sea. The energy release was equivalent to about 200 million tons of TNT, or more than 20,000 Hiroshima bombs. The resulting tsunami raced across the Pacific, striking Hawaii, Japan, and the Philippines hours later. Even distant volcanoes were triggered into activity by the shaking. It was not a single event, but a planetary one. The Earth's crust reconfiguring itself on a continental scale. What makes such an earthquake possible? In a word, cascading rupture. Most quakes rupture a single fault segment, maybe a few tens of kilometers long. But in megaquakes, the rupture doesn't respect those boundaries. When one segment fails, the stress redistribution can push adjacent segments past their breaking point, and the rupture leaps across the boundary, linking faults like falling dominoes. Each segment that breaks adds its stored strain to the process, feeding energy into the expanding front. As long as there's sufficient accumulated stress and no physical barrier strong enough to halt it, the rupture keeps going, a self-sustaining chain reaction, traveling through rock at several kilometers per second. The 2004 Sumatra-Andaman earthquake was another example of this cascading behavior on a colossal scale. It began quietly, deep beneath the Indian Ocean, as the Indian Plate thrust beneath the Burma Plate. Within seconds, a small patch of the fault slipped, then another, then another. The rupture spread northward for almost 10 minutes, ultimately extending more than 1,300 kilometers, roughly the distance from New York to Miami. Seafloor GPS measurements later revealed that some parts of the ocean floor rose by up to 5 meters. The sudden displacement of water generated one of the most devastating tsunamis in recorded history. Waves reached heights of 30 meters, slamming into coastlines from Indonesia to Sri Lanka to East Africa. More than 200,000 lives were lost. In the open ocean, the waves were barely noticeable, a rise and fall of only a few centimeters. But near the shore, that calm ripple became a wall of moving sea. All of it began with a slip no thicker than the width of a few fingernails along a fault line under the ocean. When the data were analyzed, scientists found that the rupture didn't occur evenly. It came in pulses, bursts of rapid slip followed by pauses like a heartbeat. Those pulses corresponded to distinct fault segments failing in sequence, each one adding to the total magnitude. It was, quite literally, an earthquake of earthquakes, a cascading chain that merged into one colossal event. Another of these titans struck on March 11th, 2011, off the coast of Japan, the Tohoku earthquake. At magnitude 9.0, it was one of the 5 largest ever recorded. The Pacific Plate, moving westward at about 8 centimeters, 3 inches, a year, had been pressing against the Japanese trench for centuries, bending and storing strain like a massive steel spring. When the fault finally gave way, the seafloor along the trench lurched upward by as much as 50 meters in some places, displacing an enormous volume of water. The tsunami that followed overtopped coastal defenses, flooded entire towns, and caused a nuclear disaster at Fukushima. In a grim but fascinating detail, the quake was so large it shifted the axis of Earth's rotation by several centimeters and shortened the length of the day by a few microseconds. It literally changed time, if only slightly. The physics behind these immense events lies in the interplay of friction, geometry, and energy release. Every fault has what seismologists call asperities, strong patches that resist motion. During centuries of quiet, these asperities bear the brunt of tectonic stress. When they finally fail, the stored energy is released all at once. In a normal earthquake, only 1 or 2 of these patches break. In a megaquake, almost all of them do, one after another, across an enormous stretch of fault. The cumulative slip can reach tens of meters. Imagine one side of the fault moving the length of a swimming pool relative to the other in less than a minute. That's not an analogy, it's literal motion, measured by satellite and seafloor instruments after events like Tohoku and Chile. When faults connect in this way, they behave less like individual fractures and more like a single, unified system. The boundaries between segments, once thought to limit earthquake size, become temporary suggestions rather than rules. This is what scientists call multi-fault rupture. It's one of the reasons our historical understanding of maximum possible magnitude keeps changing. Before 1960, few believed the Earth could produce an earthquake larger than magnitude 8.5. Then, Chile proved otherwise. Before 2004, it was thought unlikely that a rupture could travel more than 1,000 kilometers, about 600 miles. Then Sumatra shattered that expectation. The Earth, it turns out, is more interconnected and more capable of synchronizing its failures than we imagined. These chain reactions don't always happen along the same fault. Sometimes one major earthquake can trigger another hundreds or even thousands of kilometers away. When a large fault slips, it changes the stress field around it, either relaxing or tightening the stress on neighboring faults. If one of those neighbors is already close to failure, that tiny nudge can be enough to set it off. After the 1992 Landers earthquake in California, several other quakes followed in nearby regions over the next months, each influenced by the redistribution of stress from the first. In 2016, the Kaikoura earthquake in New Zealand ruptured more than a dozen faults in rapid sequence, some thought to be disconnected, as the energy hopped from one to the next. The pattern was chaotic but traceable, like sparks leaping between wires in a dark room. This phenomenon of connected failure extends to the entire planet. When a truly massive quake occurs, its seismic waves circle the globe multiple times, subtly modulating stress on faults everywhere. After the 2004 Sumatra quake, Sensors recorded small, triggered earthquakes in Alaska and even Yellowstone, thousands of kilometers away. They weren't destructive, but they proved a point. The Earth's crust is a single, continuous system. One rupture anywhere can, in a small way, influence the stability of faults everywhere else. The limits of magnitude, then, are not imposed by physics alone, but by geometry and by luck. For an earthquake to exceed magnitude 9.5, the Chilean benchmark, it would need an uninterrupted fault thousands of kilometers long and capable of tens of meters of slip. Such structures exist, but they are rare. Still, the planet has surprised us before. Every few generations, a new record-breaking event reminds us that the Earth is still testing the boundaries of its own strength. To live on this planet is to live on a restless machine that occasionally resets its own equilibrium. Each megaquake is a reminder that even the largest, most stable landforms are temporary. Mountains rise, coasts shift, oceans tremble. But there's a kind of order within the violence. These events follow the same rules as their smaller counterparts, only scaled up. Stress building quietly for centuries, released in minutes, redistributed again, beginning another cycle. They are not freak occurrences, but the natural punctuation marks in Earth's long story of motion. And just as one rupture can trigger another, every earthquake in history is connected to those before it, part of an unbroken chain of cause and consequence stretching back to the first continental drift. From the gentle vibrations beneath our feet to the planet's largest convulsions, the same physics rules them all. What changes is only the scale, and our sense of awe when we realize that in those moments of global motion, we are witnessing the Earth itself, remembering that it can move. For as long as people have felt the ground move beneath them, they've wanted to know one thing above all: when will it happen again? The desire to predict earthquakes is as old as the fear they inspire. Ancient civilizations searched for signs: strange animal behavior, changes in water levels, halos around the moon. Even in modern times, with satellites and supercomputers, the question remains almost the same. Can we tell, even a few hours before, that the Earth is about to move? The short answer, despite decades of effort, is still no. Short-term earthquake prediction, pinpointing the exact time, place, and magnitude of the next event, remains beyond our reach. The Earth gives no consistent warning. There are no seismic alarms that ring before rupture. What we do have, however, is a steadily growing ability to understand patterns, probabilities, and long-term risks. And while that might sound less satisfying than prediction, it has proven far more useful. In the 1970s, optimism about prediction was high. Some scientists believed earthquakes might follow measurable precursors: foreshocks, changes in ground tilt, or fluctuations in underground gas levels. In China, a series of apparent successes in the early 1970s, particularly the prediction of the 1975 Haicheng earthquake, led to national enthusiasm for earthquake forecasting. But the very next year, the Tangshan earthquake struck without warning, killing more than 240,000 people. None of the supposed precursors appeared. It was a devastating reminder that while earthquakes obey physics, their timing is chaotic. The fault may be ready to slip for decades, or may resist for centuries, and the difference between the two lies in microscopic conditions we can neither see nor measure. Modern seismology approaches the problem differently. Instead of trying to predict individual events, scientists focus on probabilistic forecasting, estimating how likely it is that a certain region will experience a quake of a given size within a specific time window. It's less about prophecy and more about probability. The question becomes not when will the next earthquake happen, but what are the odds that this area will experience a large one in the next 50 years? This shift from certainty to probability was a major turning point. Using records of past earthquakes, GPS measurements of plate motion, and models of stress accumulation, researchers can calculate the average recurrence intervals of major quakes along faults. For example, the San Andreas Fault in California has sections that tend to rupture roughly every 150 years. Some segments have gone longer without slipping, meaning stress is building. Others have recently released their tension and are comparatively quiet. These differences are reflected in hazard maps, color-coded representations showing where seismic risk is highest. They guide building codes, insurance policies, and emergency planning worldwide. A city built on bedrock might be shaded yellow. One sitting atop soft sediment and near a locked fault could glow red. The methodology is complex, but grounded in data. Scientists compile catalogs of past earthquakes, calculate the rate of tectonic strain, and use statistical models to estimate the likelihood of future rupture. In essence, they treat the Earth's faults like a series of loaded springs, each with its own probability of failure. No one can say when a spring will snap, but we can estimate how likely it is to break within a given time frame. This is the foundation of modern seismic hazard assessment, not prediction, but preparedness. And yet, the allure of true forecasting hasn't disappeared. Recent advances in computation and data analysis have opened new doors, especially in machine learning and nowcasting. Machine learning systems are designed to detect patterns that humans might miss, combing through vast datasets of seismic signals, ground deformation, and stress evolution. By comparing millions of small quakes and foreshock sequences, these algorithms can identify subtle statistical fingerprints that may precede larger events, not guarantees, but hints of elevated likelihood. In Japan, for instance, neural networks are being trained to analyze the continuous background vibration of the Earth, looking for slight changes in frequency or amplitude that could suggest an approaching rupture. It's like trying to hear a faint rhythm change in the planet's heartbeat. The idea of nowcasting builds on this. Instead of predicting a specific time, nowcasting estimates the current state of a fault, whether it's early, mid, or late in its earthquake cycle. By combining the frequency of small quakes with known recurrence intervals, scientists can assign a seismic phase to each region, analogous to a weather forecast saying, "The atmosphere is primed for storms." It doesn't say where lightning will strike, but it warns that the conditions are favorable. Applied to faults, that means identifying areas under high stress or nearing their expected release phase. Still, even these tools face the same fundamental barrier: complexity. The Earth's crust is not a single, simple system, but a web of interacting faults, fluids, and thermal gradients. Each segment influences the next. Tiny variations in pore pressure or mineral structure can change outcomes drastically. Even with perfect data, the problem might remain unpredictable in principle, what mathematicians call chaotic determinism. We can describe the equations that govern the motion, but the sensitivity to initial conditions makes long-term forecasts impossible. It's the same challenge faced in weather prediction, only vastly slower and deeper underground. That doesn't mean we're helpless. While short-term prediction may never be possible, early warning has become a remarkable success. Because P waves travel faster than the more damaging S and surface waves, sensors near the epicenter can detect the initial motion and send alerts ahead of time. In Japan, Mexico, and parts of California, automated systems issue warnings seconds before the strongest shaking arrives. It's not much, but even 5 or 10 seconds can save lives, enough time to take cover, stop trains, shut down surgeries, or simply brace. It's the difference between surprise and awareness. Some researchers are exploring whether deep learning could one day extend that window, detecting subtle signals in real time that precede P waves themselves. Others are studying electromagnetic anomalies, changes in radon gas emissions, or atmospheric disturbances that occasionally accompany major quakes. So far, none of these have yielded consistent predictive power, but the search continues. Even negative results teach us something, that the planet's machinery is smoother and less revealing than we once hoped. Perhaps that's the real lesson of earthquake forecasting, that uncertainty is not failure, but fact. The Earth's behavior is shaped by conditions so complex and interwoven that complete foresight may be fundamentally impossible. What we can do is measure, model, and prepare. We can design cities that bend instead of break, systems that alert instead of panic, and societies that understand risk rather than fear it. Prediction may remain a dream, but resilience is within reach. In the end, the impossibility of perfect foresight says something larger about our place in the world. We stand on a living planet, restless, shifting, and beyond full comprehension. The best we can do is listen closely to its patterns, learn its probabilities, and adapt to its rhythm. We may never know when the next earthquake will strike, but we know enough to stand a little steadier when it does. We live on a moving planet. Every mountain range, every coastline, every valley is evidence of motion, of rock that once flowed, buckled, or broke. And yet, we build our lives on this restless surface as though it were perfectly still. We construct cities, roads, and homes on shifting plates, confident in an illusion of permanence. But deep down, we know the ground is not still. It only rests between breaths. For engineers, that realization has shaped an entire discipline, earthquake engineering, the science of designing for motion rather than resisting it. The goal isn't to make structures unbreakable, but to make them graceful when the earth moves beneath them. A rigid building snaps under stress, a flexible one sways and survives. That principle has transformed the way we construct our world. In earthquake-prone regions like Japan, Chile, and California, skyscrapers are no longer built to defy motion. They are built to dance with it. Their steel frameworks can bend without breaking. Their foundations rest on isolators that act like shock absorbers, allowing the structure to move independently of the ground. Some towers contain enormous counterweights, tuned mass dampers, that swing opposite to the building's sway, cancelling out the motion. The Taipei 101 Tower, for instance, has a 660-ton golden sphere suspended near its top, moving on hydraulic arms to steady the structure during typhoons and quakes. It doesn't stop the building from moving, it simply turns that motion into harmony instead of chaos. Beneath cities, bridges and pipelines are designed with flexible joints, able to expand and contract. Dams and tunnels are reinforced with materials that can absorb strain rather than resist it. Even in modest homes, the principle is the same. Walls are tied to foundations, roofs to walls, frames to frames, so that the building behaves as one moving unit instead of a collection of parts tearing apart. The message from physics is clear. Survival depends not on strength alone, but on flexibility. To endure the shaking, you must learn to move with it. And while architecture adapts above ground, another frontier of human ingenuity works below, in networks of sensors and computers that listen to the planet every second of every day. These are the early warning systems, the Earth's digital nervous system. Thousands of seismometers, GPS receivers, and fiber optic sensors track the smallest tremors and the tiniest shifts. When a rupture begins, these instruments recognize the first pressure waves, the P waves, that arrive before the damaging shear waves. In the blink of an eye, they calculate where the rupture started, how big it might grow, and how long it will take for the shaking to reach distant cities. Then, they send alerts. A text message on a phone, a sound in a subway, a broadcast on television. In Japan, the system is so refined that trains automatically slow down and elevators stop at the nearest floor, seconds before the shaking begins. It's not much, just a handful of seconds. But in the language of earthquakes, that's an eternity. Enough time to breathe, to cover, to brace. In Mexico, a similar network, called SASMEX, has saved countless lives since its creation after the 1985 disaster. Even a simple siren, giving 10 seconds of warning, can mean the difference between panic and preparation. Beyond those practical systems lies something quieter but equally profound: our adaptation. We've learned to coexist with the restless Earth, to accept that motion is part of the planet's nature, not an exception to it. In places like Tokyo, Santiago, and San Francisco, earthquakes have become a fact of life, woven into architecture, education, and community response. Children practice drills, emergency kits sit ready by the door, buildings are inspected and retrofitted not out of fear, but out of understanding. It's a strange kind of peace, a resilience born not from denial, but from familiarity. In that way, earthquakes have become unlikely teachers. They remind us, more than any other natural phenomenon, of humility. They show that even our greatest achievements, our tallest towers, our most intricate machines, stand on ground that can move at any moment. They reduce certainty to seconds, and in doing so, they return us to perspective. For all our technology and intelligence, we still live according to the same physics as the stones beneath our feet. That realization can feel unsettling, but it can also be grounding in its own way. It reminds us that change is not an interruption of stability. It's the condition of it. The continents themselves are in motion. The Earth evolves through tension and release, just as we do. Every earthquake, in its terrible brevity, is the planet's way of exhaling, adjusting, restoring balance after long constraint. The same process that levels cities also raises mountains. Destruction and creation are, here, the same force viewed at different timescales. Maybe that's why, after centuries of studying earthquakes, scientists often speak about them not only with caution, but with awe. Each tremor is a glimpse of deep time, a reminder that the planet is alive beneath its crust of civilization. And if the Earth can live with its own instability, if it can tremble, shift, and still remain whole, perhaps there's something in that for us too. To be flexible rather than rigid. To understand that motion doesn't always mean loss, that uncertainty doesn't always mean danger. The Earth doesn't apologize for its restlessness. It simply moves as it must. So, as the episode comes to an end, take a moment to imagine it. The slow drift of continents, the deep convection of the mantle, the invisible hum of stress accumulating, then fading again. All of it silent, constant, and patient. Every tremor we feel on the surface is just one heartbeat in a rhythm billions of years old. We are fortunate simply to be here to listen, to witness a planet in motion, and to understand a little of how it breathes. If you've enjoyed this exploration, I'd love to know where you're listening from and what time it is there. Thank you for listening, and may the ground beneath you stay steady, even as the world continues to move.